The morning of August 19, 1943 began like any other over the flat, sun-bleached airfields of central Germany. A mechanic's shift was ending at the Rechlin testing facility, 100 kilometers northwest of Berlin, where the Luftwaffe kept its most jealously guarded secrets. Engineers in oil-stained overalls walked past rows of experimental aircraft, half-finished prototypes, stripped-down captured machines, things that were never meant to see the sky but were being made to fly anyway. Then a flatbed truck rolled through the main gate, escorted by 2 military vehicles. On the truck's trailer, partially covered by canvas sheeting that had come loose during the journey, sat a P-51 Mustang. Its olive-drab paint was scratched. One wingtip had been damaged during recovery. But the airframe was largely intact, the laminar-flow wing undamaged, the Packard-built Merlin engine still housed cleanly in its cowling. The guards who waved the truck through barely glanced at it. They had seen captured Allied aircraft before. A battered Spitfire, a shot-up Lancaster, P-38 with a burned engine. But something about the men who climbed out of the escort vehicles and walked directly to the aircraft told the senior mechanic on the morning shift that this one was different. These were not ordinary salvage officers. These were senior engineers from the Reich Air Ministry, and they had driven through the night to be here. If you've ever wondered what happens when the wrong people get their hands on the right machine, and realize too late exactly what they're holding, stay with this story. It will take you somewhere history textbooks rarely go. To understand what the engineers at Rechlin were about to discover, you need to understand what the P-51 Mustang was, and what the Luftwaffe believed it was in the summer of 1943. At that point in the war, the Luftwaffe's fighter pilots were still formidable. The Messerschmitt Bf-109G model, the Gustav, was one of the finest high-altitude interceptors in the world. The Focke-Wulf 190A series, introduced in 1941, had shocked the Royal Air Force when it first appeared over the English Channel, outclassing the Spitfire Mark V in nearly every performance category. German pilots flying these aircraft had compiled kill ratios that seemed almost impossible to Western observers. In the skies over the Eastern Front, over North Africa, over occupied France, German fighter pilots had spent 2 years doing exactly as they pleased. The American daylight bombing campaign, which had begun in earnest with the 8th Air Force in 1942, was running into serious problems. B-17 Flying Fortresses and B-24 Liberators were flying deep into Germany in tight defensive formations, relying on their combined firepower to fight off German interceptors. The theory was that the bombers could protect themselves. The reality was different. German fighter pilots had worked out that if you attacked from head-on at high closing speed, the bombers' guns could barely track you. Attack from 12 o'clock high, directly ahead and slightly above, and you could rake a B-17 from nose to tail in under 3 seconds. Losses on the deepest American missions were catastrophic. On October 14, 1943, what American crews called Black Thursday, the 8th Air Force sent 291 B-17s to bomb the ball-bearing factories at Schweinfurt, deep in central Germany. 60 bombers were shot down. 17 more were so badly damaged they never flew again. Nearly 600 American airmen were killed or captured in a single afternoon. The mission was so costly that the strategic bombing campaign against targets deep inside Germany was effectively suspended for months. The problem was escort range. The P-38 Lightning and P-47 Thunderbolt, the fighters available to the 8th Air Force in 1943, were capable aircraft, but they could not fly deep into Germany and return. The P-47, in particular, was heavy and fuel-hungry. With drop tanks it could escort bombers as far as the German border, but beyond that, the bombers were on their own. And beyond that border was exactly where the Luftwaffe wanted to fight. Into this situation came the P-51 Mustang. Or rather, into this situation came a small number of Allison-powered P-51s, which had already been evaluated and largely dismissed by American planners as a low-altitude machine. What was coming, what had already begun arriving in England in very small numbers by mid-1943, was something different. A Mustang airframe mated to a Rolls-Royce Merlin engine, built under license by the Packard Motor Company of Detroit. And that combination, as a small group of American and British engineers already knew, had produced something extraordinary. The Luftwaffe did not yet know how extraordinary. The particular aircraft that arrived at Rechlin in August of 1943 was a P-51B, one of the early Merlin-powered models. The exact circumstances of its capture are not recorded with complete certainty in surviving documents, but German recovery operations during this period were systematic and well organized. Specialized Luftwaffe salvage units, called Bergungskommandos, operated across occupied territory with orders to recover intact or near-intact Allied aircraft before they could be destroyed by Allied strafing missions or by local resistance fighters. Any aircraft that force-landed, crash-landed, or came down in a controlled emergency was a potential intelligence prize. The Mustang that arrived at Rechlin that August morning had come down in France. Its engine had developed a fault. The specific nature of the problem is not recorded, and the pilot had put it down in a field rather than attempt a channel crossing. He had been captured. The aircraft had been secured by a Bergungskommando team, disassembled at the wing roots and tail for transport, and shipped east on a flatbed railway car to the testing facility at Rechlin, where Germany's best aviation engineers waited. What those engineers were expecting was confirmation of what German intelligence had already told them. American pilots and captured American documents had described the Mustang in general terms. German observers had noted its distinctive silhouette, the long nose, the low-slung radiator under the belly, the graceful taper of the wing. Luftwaffe pilots who had fought against the early Allison-powered models in North Africa had found them unremarkable at altitude. Intelligence estimates placed the Merlin-powered version's top speed at somewhere around 400 miles per hour at altitude, comparable to the Bf-109G. Its range was believed to be significant but not yet fully understood. What the engineers at Rechlin were not expecting, what none of them were prepared for, was what they found when they began their systematic technical examination of the airframe. The first thing that stopped them was the wing. The P-51 Mustang's wing had been designed using what aeronautical engineers called a laminar-flow airfoil. The concept was not entirely new in 1943. The National Advisory Committee for Aeronautics, the American government research organization known as NACA, had been studying laminar-flow aerodynamics since the late 1930s, but no production fighter aircraft had ever been built around it. The German engineers at Rechlin knew about laminar flow in theory. They had read the same technical literature, but they had never seen it applied to a production combat aircraft, and they had never seen it executed with the precision they were now looking at. A conventional aircraft wing disturbs the air flowing over it almost immediately. The boundary layer, the thin sheet of air closest to the wing surface, becomes turbulent within the first few inches of the leading edge. Turbulent airflow creates drag. More drag means more fuel consumed for the same speed, or alternatively, lower speed for the same engine power. Engineers had understood this problem for decades. Laminar flow was the theoretical solution. If the wing surface could be kept smooth enough, and the airfoil shape designed carefully enough, the boundary layer would stay smooth and attached much farther back along the chord of the wing, reducing drag significantly. The theory was elegant. The engineering challenge was enormous. Laminar flow is extraordinarily sensitive to surface imperfections. A rivet head that protrudes a fraction of a millimeter above the wing skin. A seam that is not perfectly flush. Paint drip. An insect impact. Any of these disruptions will trigger the transition from laminar to turbulent flow, eliminating the drag reduction entirely. For a laminar flow wing to work, the manufacturing tolerances had to be tight in a way that no major air force had managed to achieve on a production line. The Rechlin engineers spent the better part of their first day examining the P-51's wing surface with instruments. They measured the height of rivet heads. They checked the smoothness of the skin panels. They analyzed the airfoil cross-section at multiple stations along the wingspan. And what they found left the senior aerodynamicist on the team, according to post-war accounts, briefly speechless. The tolerances were real. This was not a hand-built prototype. This was a production aircraft, built in a factory in Inglewood, California, on an assembly line that was producing aircraft by the hundreds. And the wing surface met laminar flow requirements that the German engineers had privately believed were impossible to achieve outside of a laboratory. If you're finding this story as remarkable as the engineers at Rechlin did, make sure you're subscribed and that the notification bell is turned on. Stories like this one, the moments when the industrial and engineering realities of the Second World War collide with what experts thought was possible, are exactly what this channel is about. The aerodynamicists moved on to the fuselage. The P-51B was a sleek aircraft by any standard. Its cross-sectional area, the size of the shadow it would cast if you shone a light from directly ahead, was smaller than the Bf-109's, despite the Mustang being a larger aircraft overall. The cooling system design was particularly noteworthy. The Merlin engine in the Mustang was liquid-cooled, meaning it required a substantial radiator to dissipate heat. Radiators create drag. On most liquid-cooled aircraft of the period, the radiator was simply hung somewhere on the airframe, under the nose, under a wing, and accepted as a necessary aerodynamic penalty. The Mustang's designer, Edgar Schmud, and the North American aviation engineering team had taken a different approach. They had placed the radiator in a carefully shaped duct under the rear fuselage, behind the wing. The duct had been designed so that the air flowing through it was accelerated by the heat of the coolant, producing a small but measurable amount of additional thrust, what engineers call the Meredith effect, after F.W. Meredith, the British engineer who had described the theoretical possibility in a 1936 paper. In practice, the Meredith effect in the Mustang partially compensated for the drag the radiator created. The net cooling drag of the P-51 was significantly lower than that of the Spitfire or the Bf-109. The Rechlin engineers measured it and then measured it again. The numbers were consistent. North American Aviation had not just described the Meredith effect. They had engineered it into a production aircraft. The structural analysis came next. A team of stress engineers spent 3 days disassembling sections of the Mustang's airframe, measuring skin thicknesses, examining joint designs, analyzing how loads were transferred through the structure. What they found was an aircraft that was lighter than it appeared. The P-51B weighed approximately 7,300 pounds fully loaded, comparable to the Bf-109G. But the Mustang carried substantially more fuel. With its internal tanks filled to capacity, the P-51B held 184 gallons of fuel. With two 75-gallon drop tanks, that figure rose to 334 gallons. A Bf-109G with a single 300-liter drop tank carried approximately 150 gallons total. A Focke-Wulf 190A series fighter carried even less. The Mustang's range, the feature that was about to transform the air war over Europe, came not from some magical technological secret, but from a combination of aerodynamic efficiency and structural discipline. The aircraft was light enough, slippery enough through the air, and fuel-efficient enough with the Merlin's two-stage supercharger at altitude that it could carry an enormous quantity of fuel and still fly faster than almost anything the Luftwaffe had. The engineers at Rechlin calculated performance figures from their measurements and the known characteristics of the Packard Merlin 61 engine. The results were startling. They projected top speed at altitude in excess of 430 miles per hour. They projected a combat radius, the distance the aircraft could fly, fight, and return from, of well over 400 miles without drop tanks. With drop tanks, the figure was nearly impossible to believe. The senior project engineer assigned to the examination reportedly walked away from his desk after reviewing the fuel consumption calculations and stood outside the hangar for several minutes before returning to authorize a second independent check of the figures. The second check confirmed the first. The Mustang, the engineers at Rechlin were concluding, could escort American bombers to Berlin and back, from airfields in England, without stopping. That conclusion landed on the desk of the Reich Air Ministry in the form of a preliminary technical report in September of 1943. The report was careful in its language. Engineers are trained to be precise and cautious, but its implications were unmistakable. If the Americans deployed this aircraft as a bomber escort in large numbers, the tactical situation that had allowed the Luftwaffe to savage deep penetration raids would change fundamentally. The report also contained a section that made for uncomfortable reading in the offices of German aviation executives. An assessment of whether the laminar-flow wing technology and the overall aerodynamic efficiency of the P-51 could be reproduced in a German fighter program. The answer, stated with the careful hedging of professional engineers who did not want to be seen as defeatist, amounted to, not quickly, not easily, and possibly not at all given current manufacturing capabilities. The problem was not knowledge. German aeronautical engineers understood laminar flow as well as their American counterparts. The problem was precision manufacturing at scale. The laminar flow wing's drag advantages depended on surface tolerances that were measurable in fractions of a millimeter. Achieving those tolerances on a hand-built prototype in a research facility was difficult. Achieving them on a production line turning out aircraft by the hundreds per month, under wartime conditions, with the material shortages and labor pressures that were already straining German industry, the engineers at Rechlin rated that as practically infeasible. This was not a question of German engineering talent. The men writing these reports were among the finest aeronautical engineers in the world. It was a question of industrial infrastructure. The American aircraft industry in 1943 had several significant advantages over its German counterpart. American factories had not been bombed. American workers were not being drafted into the military at the rate that was draining German technical workforce. American machine tool manufacturers had been building precision tooling for commercial aviation since the 1930s, and that industrial base had been converted to military production with a depth and scale that Germany could not match. The Rechlin engineers also noted something that did not appear directly in their technical report, but that colored the discussions among the engineering team. The P-51 they were examining was a production aircraft, not a prototype, not a specially prepared demonstrator. A standard production example, built to the same specifications as every other P-51B coming off the Inglewood assembly line. And it met laminar flow tolerances. One engineer, according to accounts gathered after the war, put it directly to a colleague during one of the late evenings at Rechlin. "We could design this wing. We could not build it. Not in the numbers they will build it." The performance testing began in October of 1943, after Rechlin's mechanics had serviced the Mustang's Merlin engine, painted it with German identification markings, bright yellow undersides, large black crosses, and assigned it a test designation. The pilot chosen to fly it was one of Rechlin's most experienced evaluation officers, a man with several hundred hours in captured Allied aircraft and an engineer's eye for analyzing performance rather than simply experiencing it. His first flight lasted 55 minutes. When he landed and climbed out of the cockpit, the ground crew asked what the aircraft was like. His answer was short. He said it felt like a thoroughbred, meaning it was sensitive, demanding, and capable of things that would surprise you if you weren't paying attention. Over the following weeks, the Mustang was flown against a Bf-109G and a Focke-Wulf 190A8 in simulated combat. The test flights were careful, methodical, conducted at specific altitudes and configurations to generate comparable data. The results were documented with German thoroughness and then, one assumes, filled with some degree of institutional discomfort. At medium altitudes, between 15,000 and 25,000 feet, the P-51B was faster than the Bf-109G in level flight. The difference was not enormous, perhaps 15 to 20 miles per hour, but it was consistent. The Mustang did not merely match the German fighter. It exceeded it. In turning combat, the results depended on altitude and speed. At lower altitudes, the Focke-Wulf 190 had a better roll rate. At higher altitudes, the Mustang's roll rate was comparable, and its turning radius at sustained speed was tighter than either German fighter. In a prolonged turning engagement, the kind of fight where two aircraft circle, each trying to get behind the other, the Mustang's advantages compounded. Its docile stall behavior meant a pilot could fly it closer to the edge without suddenly losing control. German pilots who had fought against it in combat had noted, according to intelligence reports, that American Mustang pilots seemed willing to pull harder in turns than Bf-109 pilots dared. They were willing to pull harder because the aircraft would warn them before it bit. The Bf-109G, pushed into a high G turn, would snap into a spin with very little warning. The Mustang would mush, buffet, tell you it was unhappy, and then recover cleanly when you released back pressure. In a gun-range turning fight, that difference in handling margin was meaningful. The dive performance was not even close. The Mustang accelerated in a dive at a rate that the German evaluation pilots found remarkable. Its laminar flow wing, which reduced drag in level flight, provided an even greater advantage as speed increased. German fighters attempting to escape a diving Mustang by pushing over and diving themselves were at a disadvantage. The Mustang would follow them down, gain on them, and close to gun range. One of the evaluation pilots wrote in his formal report that the Mustang's dive performance was superior to both the Bf-109 and the Focke-Wulf at speeds above 350 miles per hour indicated airspeed. This was not a minor observation. Diving away from a dangerous situation or pursuing a fleeing enemy, was a fundamental tactical maneuver. An aircraft with superior dive performance had a significant tactical advantage. The armament assessment was more mixed. The P-51B carried 4 50 caliber machine guns, 2 in each wing. German fighter armament by 1943 typically included 20mm cannon in addition to machine guns. A 20mm cannon shell carries substantially more destructive energy than a 50 caliber bullet. German pilots who had survived P-51 gun attacks noted that the American machine guns required more hits to destroy a German fighter than German cannon did to destroy an American one. But the Rechlin engineers noted a countervailing factor: the rate of fire. The 50 caliber machine guns in the Mustang could be fired at a combined rate that put an enormous volume of lead into a very small area of sky. If the Mustang pilot had good gunnery skills and could hold his target in the sight for even a short burst, the volume of fire was sufficient to destroy virtually any aircraft. What the 50 caliber lacked in individual projectile energy, it partially compensated for with sheer quantity. The fuel system and the Merlin engine were studied with particular attention. German engineers understood that the Merlin's 2-stage supercharger was the key to the aircraft's high-altitude performance. The Merlin 61 series maintained power at altitudes where German Daimler-Benz engines began to lose effectiveness. This was not a secret. The supercharger technology was known, but the specific implementation in the Packard-built version was examined carefully. What the engineers found was that Packard had manufactured the Merlin under license with exceptional quality control. The tolerances in the engine internals were tight. The machining of critical components, supercharger impellers, valve seats, bearing surfaces, was precise in a way that reflected both good design and good manufacturing. Rechlin's workshop assessed that they could not improve on the engine's internal design. They could study it, measure it, write reports about it. They could not easily replicate it in German factories running at full wartime capacity. By November of 1943, the Rechlin evaluation team had enough data to complete their primary technical report. The document ran to dozens of pages of performance tables, structural analysis, aerodynamic calculations, and engineering assessments. It was classified at the highest level and distributed to a small list of recipients: Senior Luftwaffe Command, the Reich Air Ministry, and a handful of German aircraft manufacturers. The conclusions were stated carefully, as is the way of engineers who are delivering news that nobody wants to hear. The P-51 Mustang, the report stated, represented a significant advance in long-range fighter design. Its aerodynamic efficiency was exceptional and reflected manufacturing capabilities that current German industry could not match in production volume. Its range at operational altitudes with drop tanks made it capable of escorting heavy bombers to any target in the Reich. Its performance against current German frontline fighters was approximately equal at medium altitudes and superior in sustained endurance engagements and dive performance. The report then addressed the question that the Reich Air Ministry most wanted answered: could German industry produce a comparable aircraft? The answer occupied 3 paragraphs, and it was one of the most consequential engineering assessments written during the entire Second World War. The laminar-flow wing technology, the report stated, was understood by German engineers. The aerodynamic principles were not in dispute, but the manufacturing tolerances required to achieve laminar flow benefits in production, not on a prototype, not on a hand-built research aircraft, but on a production line, were beyond current German industrial capability. The tooling investments required, the precision machinery, the workforce training, the quality control systems, these could not be implemented in a time frame that would affect the current conflict. A program to develop equivalent manufacturing capabilities was theoretically possible, the report concluded, but would require a minimum of 2 years and industrial investment that was not available given current war production priorities. 2 years. The war in Europe would end, as everyone in that distribution list had some reason to believe by late 1943, long before 2 years had passed. The report also noted, with the detached analytical tone of men who had been trained to state facts regardless of their political implications, that American production of the P-51 was accelerating rapidly. Intelligence estimates suggested that the monthly output of Mustangs from North American Aviation's Inglewood and Dallas factories would exceed 500 aircraft per month by mid-1944. Germany's total fighter production of all types from all factories was running at approximately 1,000 aircraft per month at that point, and it was under constant pressure from Allied bombing. The implications were arithmetical and inescapable. The Americans were building Mustangs faster than the Luftwaffe could shoot them down, and the Mustangs were getting better at shooting down Luftwaffe fighters. The gap between production rates and attrition rates was moving in one direction only. What happened next unfolded exactly as the Rechlin engineers had projected, and faster. In December of 1943, the first Merlin-powered P-51BS equipped with the 354th Fighter Group began flying escort missions over Germany. Initially, German fighter pilots who encountered them reported what their commanders wanted to hear: that the new American fighters were not significantly better than the P-38s and P-47s they had been fighting. Those reports were optimistic, filtered through the natural tendency to reassure leadership. The combat statistics told a different story. On the early long-range escort missions of December 1943 and January 1944, bomber loss rates began to fall in sectors where Mustangs were providing escort. German fighter units that had been confidently intercepting bomber formations at the outer limits of Allied escort range suddenly found that the escorts were still there, still with the bombers, still with energy to fight. There is a particular quality to the moment when a military organization realizes that its tactical assumptions have been invalidated. It does not happen all at once. The data arrives piece by piece. A mission where losses were lower than expected, a combat report from a pilot who was surprised to find himself outrun, an intelligence intercept describing American pilots discussing their aircraft's performance with a confidence that suggests they know something. The recognition comes gradually, and then, suddenly, all at once. For the Luftwaffe, that recognition crystallized in February of 1944, during what American planners called Big Week, a 6-day concentrated bombing campaign against German aircraft factories. The 8th Air Force flew nearly 4,000 bomber sorties in those 6 days. The escort was primarily Mustangs. The Luftwaffe rose to meet the bombers as they always had, flying into the escort screen in force, expecting to break through to the heavy bombers. What happened instead was that German fighter units, which had developed tactics over 4 years of combat, found that their tactics did not work. The dive-and-run attack, where a German fighter would make a high-speed pass, fire briefly, and then dive away before the escort could respond, did not succeed against Mustangs the way it had against P-47s. The Mustang could follow them in the dive. The zoom climb, where a German fighter would make a climbing attack and then continue up and away, did not succeed against Mustangs the way it had before. The Mustang could follow them in the climb. The numbers of German fighters lost in those 6 days of February were not immediately catastrophic in aircraft. Germany could replace aircraft. They were catastrophic for experienced pilots. And those could not be replaced. The Rechlin report, sitting classified in the files of the Reich Air Ministry, had predicted this with engineering precision. The P-51's endurance meant it could stay in a fight. Its performance meant it could dictate the terms of a fight. Its docile handling meant its pilots could fly it aggressively without the aircraft killing them. Combined, those characteristics meant that German tactical options were narrowed to a degree that made the mathematics of attrition work against the Luftwaffe in every sustained engagement. There is a particular kind of institutional dishonesty that military organizations practice not out of malice but out of necessity. You cannot tell your pilots that the enemy has built something you cannot match. You cannot stand in a briefing room in front of men who are about to climb into cockpits and fly toward that enemy, and tell them the truth. That the aircraft waiting for them on the other side is faster, has more range, handles better at the edge of the envelope, and is being produced at a rate that will eventually make it ubiquitous in every corner of German airspace. You cannot say that, so you say something else. You emphasize the advantages your aircraft still have. You describe the enemy's weaknesses, and the Mustang had real weaknesses, which made the selective truth-telling easier to sustain. You tell your pilots that with the right tactics, with German skill and German discipline, the situation is manageable. By the early months of 1944, the gap between what German pilots were being told officially and what they were learning through combat experience had become a source of quiet, dangerous tension inside the Luftwaffe. The pilots knew. Men who fly combat missions develop an instinct for the capabilities of what they are fighting against that no intelligence briefing can fully replicate. A Jagdgeschwader pilot who had engaged Mustangs over the Reich in January of 1944 had learned things about the aircraft that the Rechlin technical report had measured in tables and graphs. He had learned them in his body, in the stick force required to pull away, in the sight picture of a Mustang closing on him faster than he had expected, in the throttle position he had to maintain just to hold formation with an aircraft that should, according to his briefings, have been roughly equivalent to his own. He had learned, in other words, that the briefings were incomplete. Into this atmosphere of institutional half-truth and accumulating combat evidence came Hauptmann Theodor Rosarius and his unit, the Versuchsverband Oberkommando der Luftwaffe, more commonly known by the nickname that German pilots had given it, the Circus Rosarius or Rosarius Traveling Circus. Rosarius was a Hauptmann, a captain, in his early 30s, an experienced pilot who had been assigned one of the most unusual jobs in the Luftwaffe. His unit's mission was to take captured Allied aircraft, P-38s, P-47s, Spitfires, and now Mustangs, and fly them to active Luftwaffe fighter bases across Germany and occupied territory, where German pilots could examine them, sit in the cockpits, and watch demonstration flights. The purpose was entirely practical. Familiarize German pilots with the aircraft they were fighting against, so they could identify specific vulnerabilities and develop countertactics. It was, in concept, an excellent idea. In practice, by early 1944, it was producing results that no one in Luftwaffe High Command had quite anticipated. The problem was that the demonstration flights were honest. Rosarius and his pilots were professionals. When they flew a Mustang against a Bf-109 or a Focke-Wulf 190 in front of an audience of frontline German pilots, they flew it as it actually performed. They did not sandbag the Mustang to make German aircraft look better. They could not have done so even if they had wanted to. The audience watching those demonstration flights included men who had fought against Mustangs in combat and who would have immediately recognized any performance below what they had actually experienced. So Rosarius's pilots flew the Mustang honestly. And what German fighter pilots saw, standing on airfields across the Reich, watching captured American aircraft flown against their own machines, was confirmation of what combat had been telling them and official briefings had been qualifying or minimizing. The demonstrations followed a consistent pattern. At each base, the Circus Rosarius would arrive with several aircraft, typically including a P-47, a P-38, a Spitfire, and a Mustang. The local Geschwader's pilots would gather in a briefing room, where a Rosarius officer would explain what they were about to see. Then the aircraft would be parked on the flight line, and the German pilots would be allowed to walk up to them, examine the exteriors, climb into the cockpits, work the controls. The Mustang's cockpit, German pilots discovered, was notably different from the cockpits of German fighters. It was spacious, the seat was comfortable with good back support, and the pilot sat high enough that forward visibility on the ground was reasonable despite the long engine nose. The control layout was logical. The instruments were clearly marked, though in English and in American units, which required the demonstration crews to prepare translated reference cards. The gun sight was a gyroscopic sight, more sophisticated than the reflector sights used in many German fighters, and capable of calculating lead angles automatically as the pilot tracked a target. Some German pilots, after sitting in the cockpit, asked questions that the Rosarius officers found revealing. They asked about the fuel system, specifically, whether the large fuselage tank immediately behind the pilot's seat caused handling problems. The answer was yes. A full fuselage tank moved the aircraft's center of gravity far enough aft that it became unstable in certain high-G maneuvers, and American pilots learned to burn that tank down first before engaging in combat. The German pilots who asked about this already knew from combat experience that early Mustangs sometimes behaved unpredictably. They were looking for confirmation of a specific weakness. The Rosarius officers confirmed it. It was a real weakness, but they added it was a weakness that experienced American pilots routinely managed and that affected only a specific phase of flight. The demonstration flights were the centerpiece. 2 German pilots would take off in a Bf-109G and a Focke-Wulf 190. A Rosarius pilot would take off in the Mustang. The 3 aircraft would climb to altitude over the airfield, circle to allow the ground audience to establish their positions, and then engage in a scripted sequence of maneuvers designed to show performance comparisons clearly. What the ground audience saw depended on which maneuver they were watching. In the initial turning engagement, the Mustang would stay with the Bf-109 through multiple turns, neither gaining decisively nor falling behind, demonstrating that the turning performance was comparable, which was itself a revelation to pilots who had been told the Mustang was primarily a fast, straight-line aircraft that could be defeated in a turning fight. In the rolling sequence, the Mustang would outroll the Focke-Wulf at medium speed significant, because the Focke-Wulf's roll rate had been one of its most celebrated advantages when it first appeared in 1941. In the acceleration sequence, the Mustang would pull ahead of both German fighters in sustained level flight acceleration. In the dive, the Mustang would open distance from both German aircraft and continue pulling away as speed built. The silence that typically followed these demonstrations, according to accounts from German pilots who attended them, was not the silence of surprise. It was the silence of confirmation. The pilots watching had, most of them, already fought against Mustangs. They had already experienced, in combat, the aircraft performing in the ways they were now watching in controlled demonstration. Zircus Rosarius was not showing them something new. It was showing them official acknowledgement of something they already knew. That acknowledgement was, in its own way, more unsettling than the original combat experience. It meant the performance was real, documented, and recognized by the Luftwaffe's own test pilots. It meant the aircraft they had been fighting against was genuinely as capable as it had seemed. It was not luck or unusual circumstances in specific engagements. It was an aircraft. Meanwhile, at Rechlin, the engineering work had continued beyond the initial evaluation. A second Mustang, a P-51, be captured in France in mid-1944, similar to the aircraft that would later be identified in post-war records as the aircraft flown by Lieutenant Thomas Fraser, arrived for additional analysis. By this point, the engineering team had already completed their primary assessment, but there were specific questions that had emerged from the initial report that required additional investigation. The most important of these involved the laminar flow wings manufacturing tolerances and whether any aspect of the technique could be incorporated into existing German aircraft programs without requiring the full industrial infrastructure overhaul the initial report had identified as impractical. The answer, after several months of additional analysis, was essentially negative. The laminar flow benefits were not separable from the precision manufacturing. You could not take the airfoil shape, reproduce it in a German factory using existing tooling and quality control processes, and expect to achieve laminar flow. The airfoil shape and the surface finish were a system. Either you could manufacture the system to the required tolerances, in which case you got the drag reduction, or you could not, in which case you had an airfoil shape that provided no particular advantage over conventional designs and might actually perform worse in certain respects, because the laminar flow airfoil section was optimized for conditions that assumed laminar flow existed. Without the smooth boundary layer the wing was designed around, you had neither the low drag characteristics of a laminar flow wing nor the generous stall behavior of a conventional wing. You had a wing that performed adequately but was optimized for a manufacturing quality that you had not achieved. The Rechlin engineers wrote this up carefully. The conclusion was stated as a technical finding, not a policy recommendation. But the technical finding had a policy implication that was impossible to ignore. Germany could not build the wing that made the Mustang what it was. Germany could build excellent aircraft. The Bf 109K4, which entered service in late 1944, was in many respects the finest version of a design that had been continuously refined since 1935. The Focke-Wulf 190D9, the Dora, was a superb high-altitude fighter. Germany was also developing jet aircraft, the Messerschmitt 262, which would prove faster than any propeller-driven aircraft and which represented a genuine technological leap. But the propeller-driven aircraft that Germany could build and build quickly, in the numbers required, could not be made to replicate the specific combination of characteristics that made the Mustang uniquely dangerous. The laminar flow wing, the Meredith effect cooling duct, the Packard Merlin with its two-stage supercharger maintaining power at altitude. These were not individual features that could be copied in isolation. They were a system, and the system had been designed and manufactured to a standard that German industry, under wartime conditions, could not match. German aircraft companies received copies of the Rechlin analysis and were asked, in effect, to respond. Could any of this be incorporated into current or planned designs? Focke-Wulf studied the laminar flow sections extensively. Their engineers concluded what the Rechlin team had already concluded. Achievable in a laboratory, not achievable in production. Messerschmitt reviewed the cooling system analysis. Their engineers noted that the Meredith effect was theoretically applicable to German liquid-cooled designs, but that implementing it to the degree achieved in the Mustang would require redesigning cooling systems that were already in production, a disruption to manufacturing that could not be justified given the urgency of maintaining output. The answer from German industry, delivered in the careful language of engineers reporting to a government that was not always receptive to unwelcome findings, was the same answer the Rechlin engineers had already given. We understand it. We cannot build it. Not now. Not at scale. Not in time. The summer of 1944 brought events that made the engineering discussions at Rechlin feel simultaneously more urgent and more academic. On June 6, 1944, Allied forces landed in Normandy. On June 6, Lieutenant Thomas Fraser force-landed his P-51B in northern France and was captured. His aircraft, the one nicknamed Jerry, was recovered by a Bergungskommando team within hours and shipped to Rechlin, arriving on June 8. By June 10, Rechlin's test pilot Hans Fay had been assigned to have it ready to fly within 2 days. The Luftwaffe's hunger for information about the Mustang had not diminished even after a year of evaluation. If anything, the pace of Mustang encounters in the air over Germany had made the engineering and tactical questions more pressing. Phase flights in Fraser's Mustang produced data consistent with what the earlier evaluations had already established. The aircraft performed as projected. It behaved as the Rechlin team had characterized it. The laminar-flow wing worked as the aerodynamicists had calculated. Nothing in phase test flights contradicted the findings of the original 1943 assessment. But the context in which those findings were now being received had changed completely. In August of 1943, when the first Rechlin report was filed, the Luftwaffe was a formidable force that had been losing ground gradually. The strategic situation was serious but not yet dire. German fighter pilots were still experienced veterans, the production lines were running at high capacity, and the war in the East, while going badly at Stalingrad, had not yet produced the cascading disasters that would follow. By June of 1944, the context was different in almost every dimension. The Soviet Union had launched Operation Bagration, which would virtually destroy Army Group Center in a series of offensives that rivaled Stalingrad in scale. Allied forces were fighting their way through Normandy toward the German border. American strategic bombing, now protected by Mustang escorts to any target in the Reich, had destroyed or severely damaged dozens of key German industrial facilities. Oil refineries at Ploesti, Luna, and Bolin had been hit repeatedly. German aviation fuel production was falling. Without aviation fuel, even excellent aircraft were useless. And the Luftwaffe was bleeding pilots at a rate that no training program could match. In the 6 months between January and June of 1944, the Luftwaffe had lost approximately 2,300 experienced fighter pilots killed, captured, or permanently disabled. That figure represented the accumulated expertise of years of combat flying. Pilots who had learned, through dozens of missions, how to survive and how to kill. Replacing them with graduates of an accelerated training program that had been cut from 200 hours to sometimes fewer than 100 hours of flight time was not a replacement in any meaningful sense. It was substitution of experienced men with inexperienced men in the same cockpits. The Rechlin engineering report on the Mustang had noted, back in 1943, that the aircraft's docile handling near the stall and its forgiving stall recovery gave inexperienced pilots a margin of safety that the Bf-109 did not provide. An American pilot with 100 hours of training could fly the Mustang in combat at high G-loads and recover from mistakes that would have killed him in a less forgiving aircraft. The same pilot in a Bf-109, which would snap into a spin in a stalled turn with minimal warning, had a much shorter survival expectancy. That observation, made as a technical note in a performance evaluation, had turned out to be a strategic insight. As the experience gap between American and German pilots widened through the first half of 1944, the Mustang's forgiving handling characteristics became more valuable with every month that passed. American pilots who were less experienced than their German opponents were flying an aircraft that compensated for inexperience. German pilots who were less experienced than their predecessors were flying aircraft that punished inexperience. The attrition mathematics of the air war over Germany were not just a function of aircraft performance. They were a function of aircraft performance interacting with pilot experience, and both variables were moving in favor of the Americans simultaneously. There is a moment in the examination of any historical catastrophe where you can identify the point at which the outcome became, if not inevitable, then extremely difficult to reverse. For the Luftwaffe, that point arguably came not on a specific date or in a specific battle but in a series of engineering offices and test facilities at Rechlin, at the Focke-Wulf Design Bureau, at the Messerschmitt facilities in Regensburg, where men who understood aircraft sat down with the measurements from a captured P-51 and worked through the implications. The implications were that the Americans had solved a manufacturing problem that Germany had not solved. They had taken a theoretical aerodynamic concept, laminar flow, and implemented it reliably in a production aircraft. They had done this at a moment when the aircraft's range requirements made aerodynamic efficiency more important than it had ever been in a single-engine fighter. And they had done it in a country with an industrial infrastructure that could produce the result at a scale, eventually more than 15,000 Mustangs built, that made individual aircraft losses strategically irrelevant. Germany could not copy it. Not the wing. Not the cooling system efficiency. Not the combination of those characteristics with the Merlin engine's high-altitude supercharger performance in an airframe light enough to carry the fuel load that made the range possible. Each element was technically comprehensible. The combination was industrially unreachable. This was the conclusion that sat, classified and uncomfortable, in the files of the Reich Air Ministry through the summer and autumn of 1944. And it was the conclusion that gave the Rechlin engineers' work a particular character. The most thorough, most honest, most technically precise evaluation of an enemy aircraft conducted by any air force during the Second World War, produced by men who understood exactly what they were looking at and understood with equal clarity that there was nothing they could do about it. By late 1944, the Mustang had arrived in numbers that made its presence definitive rather than significant. The 8th Air Force in England, the 15th Air Force operating from Italy, and the tactical air forces supporting ground operations in France and later Germany, all were heavily equipped with P-51s. More than 800 Mustangs would fly on a single day's missions in the final months of the war. German radar operators tracking those formations were tracking aircraft that, as the Rechlin engineers had calculated, had the range to go anywhere in Germany and come home. There was no safe corner of the Reich from Allied air power. General Karl Spaatz, commanding the United States Strategic Air Forces in Europe, had authorized a campaign specifically targeting German oil production in the spring of 1944. The Mustang's range made that campaign possible. Synthetic oil plants at Luna, Brucks, Blechhammer, and Politz, facilities deep inside Germany and occupied Poland, were struck repeatedly. By September of 1944, German aviation fuel production had fallen to less than a quarter of its January level. Aircraft that had been built, pilots who had been trained, were grounded for lack of fuel. A Bf-109K4 sitting on an airfield in eastern Germany with empty tanks was not a fighter aircraft. It was a target for the next Mustang sweep that came through. And the Mustang sweeps came regularly. General Jimmy Doolittle's directive to American fighter pilots: pursue the enemy, destroy them in the air, destroy them on the ground, do not simply defend the bombers, had been operationalized into a campaign of airfield strafing that destroyed German aircraft on the ground faster than the factories could produce replacements. More American pilots were lost to ground fire during strafing attacks than in air-to-air combat in the final year of the war. They accepted those losses because the tactical results were decisive. The Rechlin engineers who had examined the Mustang and written that it could not be copied had been right in every technical particular. They had also, without intending to, described the shape of Germany's defeat. If you cannot build what the enemy has built, and the enemy can build it faster than you can destroy it, then the attrition equation works against you indefinitely. That is not a tactical problem. It is not a problem that courage or skill or doctrine can solve. It is an industrial and engineering problem, and by the time the Rechlin evaluation team wrote their final assessment, the industrial and engineering gap it described was already wider than any German program could bridge. The men who wrote those reports survived the war. Several of the senior Rechlin engineers were interviewed by American, British, and Soviet intelligence teams after Germany's surrender in May of 1945. The interviews were extensive. The Allied teams wanted to understand German aircraft development in detail, what had been tried, what had worked, what had failed, and what Germany had learned about Allied aircraft during the war. The assessments of the Mustang that emerged from those post-war interviews were consistent with what the Rechlin reports had said at the time. Several engineers confirmed that the laminar flow wing manufacturing problem had been identified in 1943 and had never been resolved. Several confirmed that the range calculations from the first evaluation, the ones that had projected Mustang escort capability to Berlin and back, had been accurate and that those projections had been reported to Reich Air Ministry, where they had been received with what one engineer described in the careful language of a man speaking to Allied interrogators as some skepticism. The skepticism had not changed the facts. The Mustangs had appeared over Berlin in the spring of 1944, exactly as the engineering calculations had predicted. When Hermann Göring, the Luftwaffe's commander, reportedly said upon seeing Mustangs over Berlin that he knew at that moment the war was lost, he was articulating in emotional terms what the Rechlin engineers had stated in technical terms a year earlier. The engineering report had simply arrived at the conclusion before the history did. The pilots of the Zircus Rosarius continued their demonstration tours through the autumn of 1944. The audiences changed, frontline units were being moved and reorganized constantly as the military situation deteriorated. But the demonstrations remained consistent. German pilots came to airfields, watched Mustangs fly against their own aircraft, sat in the cockpits, and left with a clearer understanding of what they were facing. Some of those pilots were killed in the weeks after attending the demonstrations, flying the Bf-109 and Focke-Wulf aircraft that the demonstrations had shown to be outmatched at range and in endurance. Some survived the war and later described the demonstrations in memoirs and oral histories that became part of the historical record. Their accounts are notable for a quality of honesty that the official wartime communications sometimes lacked, an acknowledgement that by the time the Rosarius demonstrations reached their peak, the pilots attending them already knew what they were going to see. The demonstrations confirmed knowledge that combat had already provided. They were official recognition of a reality that had been accumulating for a year. One Jageschwader pilot, recounting his experience of an airfield demonstration in the autumn of 1944, described the moment when the Mustang accelerated away from the Focke-Wulf in a simulated level flight chase. He said that several pilots around him nodded, not in surprise but in the particular way that people nod when something they already believe is stated clearly in front of them. They had seen that acceleration from the other side of the gun sight. Now they were watching it from the ground. The experience did not change what they knew. It simply confirmed it officially in front of everyone. Lieutenant Thomas Fraser spent the duration of the war in German prisoner of war camps. He had been captured on June 6, 1944, the day the Allied landings at Normandy began. A historical coincidence that meant he missed the entire final phase of the war in the air, the phase in which everything the Rechlin engineers had calculated about his aircraft's impact came to pass. He was liberated in the spring of 1945 and returned to the United States. Years later, when researchers began tracking the wartime fate of captured Allied aircraft through German records, Fraser learned what had happened to his P-51B, the one he had called Jerry, after he walked away from it in that French field. It had been shipped to Rechlin. It had been repaired, repainted, and given German markings. It had been flown by Hans Fay in a series of test flights that produced data consistent with the earlier Rechlin evaluations. It had then been transferred to the Zircus Rosarius inventory and flown to multiple Luftwaffe bases as part of the demonstration program. And it had eventually been lost. German records indicate the aircraft was written off in December of 1944. The specific cause not recorded with certainty in the documents that survived. Fraser's service record noted simply that he had lost one aircraft to mechanical failure over enemy territory. It did not note that his aircraft had contributed to some of the most consequential engineering analysis of the air war, analysis that had confirmed, in the offices of Germany's own aeronautical establishment, that the Luftwaffe was facing an aircraft it could not match and could not replicate. The aircraft that had forced Fraser down with a cooling leak had, in German hands, helped write the technical case for why Germany could not win the war in the air. There is a particular quality to that irony. The aircraft's vulnerability, the sensitive liquid cooling system that was the Merlin engine's most significant tactical weakness, the weakness that had brought Fraser down in the first place, was the thing that delivered it to Rechlin. And Rechlin's engineers, given the aircraft to analyze by that accident of war, had confirmed that despite that vulnerability, despite every weakness the P-51 possessed, the combination of capabilities it represented was beyond Germany's ability to answer. The cooling leak that ended Fraser's mission began the engineering evaluation that documented the Mustang's strategic significance. What the Rechlin engineers had concluded in 1943 and early 1944 was not a secret that the Luftwaffe kept entirely to itself. Versions of the assessment filtered through to fighter units in the form of tactical guidance. Pilots were told the Mustang's strengths, its range, its dive performance, its roll rate at medium speed, and advised on how to engage it at maximum disadvantage. From above, at high speed, in a single firing pass, never in a sustained turning engagement, never in a chase. The advice was sound as far as it went. Against an inexperienced Mustang pilot, those tactics gave a German pilot a fighting chance. Against an experienced Mustang pilot with full situational awareness, altitude advantage, and radio contact with his wingman, the same tactics were considerably harder to execute. By late 1944, the average American pilot flying Mustangs over Germany had more total flight time than the average German pilot he was fighting against. He had more combat missions. He had better situational awareness from the bubble canopy of the P-51D, which had entered service in mid-1944 with its 360-degree visibility. And he had the knowledge, derived from the same pattern of combat experience that his German opponent had, that his aircraft could disengage from any fight it did not like and could stay in any fight it chose. That last characteristic, the freedom of action that came from superior range and comparable or superior performance, defined what the Mustang meant for the air war in a way that performance tables alone could not fully capture. It was not just that the Mustang was fast or maneuverable or had good range in isolation. It was that it combined all of those characteristics in a single aircraft, which meant that the pilot flying it always had options. He could chase or he could disengage. He could climb or he could dive. He could escort the bombers or he could go looking for a fight. He could fly to Berlin, fight there, and come home. The tactical flexibility that came from those combined capabilities gave American pilots something that is difficult to quantify but impossible to overstate: confidence. The Rechlin engineers had measured the laminar-flow wing and the Meredith effect cooling duct and the Merlin supercharger and the fuel capacity. They could not have measured the cumulative effect of those characteristics on the psychology of the men flying the aircraft versus the men fighting against it. But the accumulated evidence of 1944 makes it clear that the effect was real and significant. American pilots flew Mustangs with the confidence of men in an aircraft they believed in. German pilots fought against Mustangs knowing, from combat experience confirmed by their own Air Force's technical evaluations, that they were fighting something that could not be answered with what they had. That asymmetry of confidence, compounding month by month through the last year of the war, was perhaps the final thing that the Rechlin engineers' report had failed to capture. Not because they were negligent, they were thorough and honest, but because it was not the kind of thing that appeared in performance tables or structural analysis. It was the human dimension of the engineering reality they had documented, the experience of fighting, and of being fought by an aircraft that had been assessed by your own experts as impossible to copy. The war in Europe ended in May of 1945. The Luftwaffe that had dominated European airspace in 1940 through 1942 had been destroyed, not in a single decisive battle but in the accumulated attrition of years of combat against an opponent whose industrial capacity and aeronautical engineering had, by 1943, produced something the engineers at Rechlin had recognized and documented with precision. The P-51 Mustang's final wartime record was unambiguous. More than 15,000 were built. P-51 pilots were credited with destroying approximately 4,950 enemy aircraft in aerial combat in all theaters, more than any other Allied fighter type in the European theater. They had escorted bombers to Berlin, to Munich, to Brux, to Ploesti, to targets across the entire Reich and beyond. They had strafed airfields across Germany, destroying thousands of additional aircraft on the ground. They had contributed to the destruction of German aviation fuel production that grounded the remaining Luftwaffe in the war's final months. None of that had been inevitable. The P-51 could have been a minor footnote, a capable low-altitude aircraft used for reconnaissance, significant in secondary theaters, never achieving the laminar flow manufacturing standards that made it exceptional. Ronald Harker's suggestion to install a Merlin in a Mustang airframe could have been ignored, or tested and rejected, or approved too late. Thomas Hitchcock's report from London could have been filed without action. The Packard Motor Company's license-built Merlin production could have fallen short of quality standards. Any number of factors could have prevented the specific combination of capabilities that the Rechlin engineers examined and found unreproducible. They did not prevent it. The combination existed, worked as designed, and arrived in operational service at the exact moment the strategic bombing campaign needed it most. That was not luck. It was the result of decisions made by engineers, test pilots, production managers, and military officers over several years. But the timing was close enough that the margin is worth acknowledging. The post-war years brought the Rechlin engineers and test pilots back into the world of aviation under different circumstances. Germany's aircraft industry, like the country's broader industrial capacity, had been largely destroyed or dismantled by 1945. Several former Rechlin personnel were recruited by Allied programs, American, British, and Soviet, that sought to exploit German aeronautical expertise. The knowledge these men carried was considered valuable enough that their wartime service was, in various cases, overlooked in favor of their technical capabilities. Hans Fay, who had flown Fraser's Mustang at Rechlin in June of 1944, survived the war and was interviewed extensively by American aeronautical intelligence teams. His evaluation of the P-51 was consistent in the post-war interviews with what his contemporaneous reports had said. The aircraft was exceptionally well designed, the laminar-flow wing represented genuine engineering achievement, and the combination of performance characteristics made it the finest long-range fighter of the war. He expressed no bitterness about having evaluated an enemy aircraft. He had been an engineer and a test pilot. His job had been to analyze aircraft. He had analyzed it accurately. The broader question that his wartime reports raised, whether Germany could have developed equivalent technology under different circumstances, has been debated by historians and aeronautical engineers since the 1940s. The weight of evidence suggests that the answer is no, not within any time frame relevant to the war's outcome. The laminar flow manufacturing problem was real and not trivially solvable. The American production capacity that could implement the solution at scale was a product of industrial infrastructure that Germany did not possess and could not have built quickly enough. The combination of the right aerodynamic concept, the right engine, and the industrial capacity to build both at scale was American, and it was American for reasons that went deeper than any single technical decision. What Rechlin's engineers had documented was the visible surface of an industrial and engineering competition that the United States had won before the P-51 Mustang ever left the ground in combat. The aircraft was the evidence. The engineering reports were the acknowledgement. The air war over Germany was the outcome. If this story has shown you anything, it is that wars are not decided only on battlefields. They are decided in engineering offices, on factory floors, in the decisions made by production managers about manufacturing tolerances, and in the quiet conclusions of test pilots who land after evaluation flights and write, with professional precision, that what they have just flown cannot be replicated. The Rechlin engineers understood this. They wrote it down, and the history of the air war over Europe confirmed, month by month and mission by mission, everything they had put on paper. The P-51 Mustang did not win the air war alone. No single aircraft, no matter how capable, could have done that. But it provided, at the critical moment, the capability that made every other element of the Allied air campaign possible. The ability to go anywhere, protect anything, and engage on terms favorable to the attacker. Germany's own engineers assessed that capability, measured it, calculated its implications, and concluded that it could not be answered. The aircraft the Luftwaffe called impossible to copy turned out to be exactly that. Impossible to copy and impossible to stop. That is the story of what happened when Germany's best aeronautical engineers sat down with a captured American fighter, measured it with precision instruments, and discovered that the gap between what they understood and what they could build was, in the end, the gap between winning and losing.